Hi, let's work in this second tutorial now related to this curvature correction. So we will work in the static mixer. So here you have mesh, everything. So let's take a look at this instruction, what I want you to do. So basically we have this geometry and let's set this value. So we're going to run, just choose any turbulence model up to you, and we're going to see the influence in the in the turbulent viscosity, but now using the curvature correction in this geometry. Okay, so here that we know, or you're going to see that here we have an storm vortex here. So basically this is what we have. Here we have flow entering 300 kelvins is velocity, so we are going to need to set up the energy equation. Here you have also flow entering, okay, and then we have the outlet. Quite simple as usual. We'll ask you to set up some monitors, and basically this is what we're going to have. Okay, so see that you have the mixing here, and as you plot the stream line, so we'll show you how to plot this one. See that you have this strong vortex here in the middle, also you see here. So this is the idea that this curvature correction, when you have this kind of system, a lot of swirl here, they can improve a lot your results. Okay, so let's play with this case, get the geometry. So here we have the mesh, okay, so already generated, but you have the geometry also, the edges, so you can generate different meshes, okay, different boundary layers. So in this case our approach is wall modeling, so I will recall the Y plus is something around 50 or 60. So let's go through the case setup. So as usual, go general, pressure basis, steady, then you go into model. So feel free to choose any model. I will run a few cases using the K epsilon standard because they have wall functions, and enable production limiter. Do not use for the moment the curvature correction, then we're going to see that results. And also enable the energy equation, okay? Nothing else to do here. Then you go to materials, and here you have air, so you choose your air properties. So for the moment run everything constant, okay, so we don't have any influence of temperature on your density or viscosity, but everything constant. And in materials, as user, remember you have different materials, you can choose your material, but here the default values are okay. And then we go to boundary conditions. So in boundary conditions we are going to have this setup. So see that already named the patches. So in the inlet call you will put the temperature 300 kelvins, as you recall. So you see temperature 300 kelvins, you have the velocity, and then we have worked this out, so you know how to set these values. Okay, so you have better estimate with K for KNX. So at the end, feel free to put it. So in my case I will use these values, so I know that my diameter there is 1 meter, so we can confirm that you have the drawings. Okay, so see that your diameter, okay, 1 meter, okay, but so you put your values. The same will you do for the HUD. So in the HUD we have the velocity inlet, you set up velocity, your values again, and then your thermal boundary conditions. At the outlet is a usual pressure outlet, so you only give the default values are okay, you only give backflow conditions, so the default values are okay, and the rest are walls. So here you have two walls because, well, when I was generating the mesh I didn't group everything together, but it's not a problem, okay? So we don't need to do anything else here. And then we go to the tab here where we have the solution method. So here I will show you, because there was a question that raised during the lectures, different methods. So I will show you a little bit the behaviors in the different methods. So in theory you should get the same solution, but as the methods are different, then you will have different convergence rates, so it's quite difficult to assess everything. But I have been telling you that probably the coupled version is the best one, but sometimes it's not the best one because coupled can be really expensive. The cost per iteration is really high, so sometimes it's simple, it's better. So this is a nice case. You can play we saw this configuration already did it, so I will show you different behaviors so you can get an idea. So you can run the first case using the simple, and let's go all this setup, everything, let's use second order accurate, okay? So by default also Fluent, it will propose you'll see that the turbulence quantity is first order when that is okay, but let's go everything second order accurate. Remember that momentum has to be at least second order for good accuracy. So let's use this setup. And by the way, the simple, okay, so you have your setup, then controls. We have seen a tutorial how to control this. In this case, default values are okay. So you create also, if you have this, you create your monitors, reports the definition. So we need the usual y plus value in our walls, mass flow at the outlet, okay, just at the outlet, do not do, or probably, let me check, okay, you have the weighted temperature, okay, you see here, weighted temperature at the outlet, so it's a area weighted average just at this one. Then we have the mass flow, okay, it's computed in all surfaces, in inlets and outlets, so it should be close to zero because the method is conservative. We don't have any source terms. You see the y plus is computed at all walls, and then we have the average area weighted average at the pressure outlet of what velocity magnitude. So if you have some other monitors, so probably you can put some probes inside the domain to measure velocity. Okay, it's up to you, but these are enough in this case. Then monitors, so let's use the full residuals. Okay, no problem here, nothing else to do, and let's initialize. Okay, so first run using initialization method, the uniform initialization method, and then we are going to play with non-uniform hybrid initialization. We're going to see the influence. So here let's use these values. Okay, so see that we're computing from the inlet, the hot inlet, the one with these values, velocity, this temperature. So let's use a uniform initialization all around. Okay, so initialize, and then we can run the solution. Okay, so put 100 iterations there, and let's launch it, and let's see the behavior. Okay, so probably this will take something like 1,000 iterations, 1,200 iterations, I don't recall, but let's monitor this behavior, and then I have many other solutions, and I'm going to just to compare right ahead. But just this one is just to show you the whole process, and then we're going to do some post-processing. So I will launch, and then probably in 10-20 minutes we keep working on this one. So press calculate, and voila, off you go. Okay, so we're back. So see that in my case it converged in about 747 iterations. So, and remember that usually these monitors are not a true indication of your convergence. You should also monitor some integral quantity. So see, this is why we add these monitors. So see here that we have the temperature at the outlet, so see that it's very flat, it's not oscillating. Then we have the mass flow, so it should be balanced out, so it should be close to zero. You have here the report in the text user interface. Then our y plus, okay, so it's still oscillating, but it's showing us that yes, our mesh is about y plus 60. And then we have the average velocity at the outlet, sorry. So see that at the beginning it's kind of flat, but then you have this destabilized, and then see here that you are reaching this area here. So I will not go, so this is here, you can see that maybe would be a good idea to keep running this this simulation to see what happened with this monitor, okay? Because it seems that it still is it haven't stabilized. Okay, so let's do something and let me run it a little bit more to see what happened with this one. So remember that if you try to run now, it will start immediately because you reach these monitors. But let's do something, and you can go in residuals and you can disable all these monitors, okay? And let's run for another 500 iterations, and let's see what happens, okay, with the so now we're interested in this one. We know that we reach our linear solvers tolerances, but we still have some kind of an unsteadiness in one field. We need to wait for this one to reach a steady state. It becomes flat. So press calculate, and let's see what happens in a few minutes. Okay, we're back. So we run additional 500 iterations and see that the behavior here, it was kind of previously converged about here, so it wasn't fully flat. Then we let it run and see that it's getting flat. It might be oscillating a little bit. So this is part of the CFD that is not only looking at this one. So see that this one are converging very well in a monotonic way, but then you monitor some other quantities and you see different behaviors. So let's say that we can stop here. Also take into account that we here, as you're going to see, we're going to have a vortex, so probably the oscillations, but also take the outlets. We're going to expect that. So we have a solution. Let me save it here also. So let's do now some post-processing. Okay. So see here we were running with no curvature correction. So I prepare many solutions. I will show you, but then it's up to you to run them and compare. So this is a simple pressure velocity case. Coupling, we're using the simple method. So now remember that these curvature corrections have an influence on our viscosity, turbulent viscosity to be specific. So let's plot that quantity in a cut plane. So in the case that you have already generated a few cut planes, I will show you also how to generate those. And let me, okay, change that, and I want to plot it here, okay? So see here that we have turbulent viscosity here, and this is what we have. So in the area where, in the region where we have that vortex, see that we are going to have that vorticity, the turbulent viscosity generation. So if I want to plot some streamlines, you can go here, past lines. Already there is one there, but they make. Okay, let me take this one. So it's a press displace and release. Okay, see that I'm releasing from all surfaces. Okay. And see that what we have here. So what I was telling you that you have here the concentrated vortex. Okay. So see here. So this is very typical. This you have it in this kind of application. This is static mixers or cyclone mixer or mixing chambers. And the problem here is that sometimes when you have this strong swirl tolerance models, the classical viscosity models may give you problems, and this curvature correction will take into account this one, so it will try to generate less turbulent viscosity. So if I go, let me go back to this cut plane, put it here now again, and we have it there. So this is one solution, and now let's compare this one where we have the simple method, okay, with no curvature correction, and I have it all of here. So see that now when I use the curvature correction, this is our solution. So pay attention that we're using the same scales and see that how it's producing much less Turbulent viscosity than in this one. But also we have here many solutions that we're comparing different methods, and then we're going to see that you see that we have different methods, different convergence rates. So each convergence rate, so in one case will converge in 2000 iterations, and in the other one didn't converge at all, but I let it run for 3000 and see that we have different behaviors. But what is common in all of them, so this is the one we just run, okay? Then we have this one, which is a couple solver, okay, uniform initialization with and here, okay, here I have curvature correction, by the way, okay, so this is curvature correction, no curvature correction, so see that we're producing a lot excess of turbulent viscosity. So we have the couple turbulent correction, then we go to another one here, a couple, but this one we have a second version with another initialization, and see that we have a very different behavior. Again, we have curvature correction, and the different here, let me recall here that I think, okay, it is the time scale factor. So see that here we're running with a time scale factor of 10. Okay, so we know that this time scale factor is related kind of to the time step. So we're adding too much diffusion in this case. Instead, in C3, we were running with a time scale of 0.1, so it was very accurate. So the difference that you see in these two are this one. So here we have the same couple solver, same uniform initialization, time scale factor of 1. Okay, so you see that we have this behavior. We have always the curvature correction. Okay, so probably you will see that it's large, but as you compare with the original, the base case, okay, see that this is a lot, no curvature correction. Okay, and then we keep here the simple method, and here we're using a non-uniform initialization. So just to be clear, the full multigrid initialization. So see that every single one have different behaviors. Okay. But all of these that we have here, curvature correction, and the one with no curvature correction, you have this one. So if you can run this one, we are running simple, and you run this one with the couple, you will get something similar, okay? So this is the idea, and this is this curvature correction. So the curvature correction, remember that you enable that here. So now you can rerun this one, put it here, and you don't need to do anything else, okay? That correction will add a limiter to avoid this overproducing, in this case, the too much turbulent viscosity. But now we have this, and let's take a look probably at the convergence monitors of each of these cases that I prepare. So let me plot it here, plot, okay, plot here also, because this is also interesting behavior that we're going to see, and I have it. Here, then I go here, plot, and then I go here, plot, and this one. Okay, so we have residuals here, and let me plot this one, and just to show you how also we have the last one. So this one here is the Reynolds stress model, so we addressed this one in the last lecture. So see here that we're seeing here the turbulent viscosity, which is related to the additional equations that you are solving, which are the epsilon equation, and also you have the K equation that you take the trace of the Reynolds stress. Okay, but when you analyze this one, you shouldn't look at this too much. Instead, you should look at the information of the Reynolds stresses, because you have that information available. So you have it here, you go, and this, you have all your Reynolds stresses. So look at that information instead of this viscosity. But in any case, see that the behavior is also different in this one. Okay, probably it's not the right field to look, but you have different. And for Reynolds stresses, you don't have any curvature correction, okay, because in your equations you have already these anisotropic behaviors contained. So if we look at the different convergence monitors here and different methods, so look at that, what we have here is the simple method, uniform initialization, and actually this case converging about 1000 iterations. Okay, see that it is converging to my tolerances here, but when you look at the integral quantities, okay, you see here the behavior, and this is the importance that why you need to monitor these quantities. So see that in this case, it might be needed to iterate a little bit more, but let's say that it's reaching that flattening point and about, let's say, 700 iterations, okay? So this is the simple case with the non-uniform uniform initialization, then the same simple case, non-uniform initialization, and see that now using a non-uniform initialization is taking longer to converge, okay? So see that even initial conditions can have a very strong influence in your final solution, okay? So probably you might think that a non-uniform solution would be better, but in this case, it's not the situation, okay? So see, it's taking longer. And then as you compare quantity, integral quantities, see that you have a very unsteady behavior at the beginning that you don't see in this one where you have the uniform initialization. So you will have a strong initial transient here. But then everything is stabilized, and it's likely that these two solutions might reach, in average, approximately, let's say, the same value. So this was the non-uniform, but then let's move to the other one, which is this one. So now this is the couple solver, okay? So this is the one that I highly recommend to use, but it's not always the best solver. Some cases it might be better to go to the simple or simple C or P. So, and maybe as you run this case, is you measure the cost per iteration, you will realize that the couple is very costly per iteration. It costs much more, but we're going to see the behavior that you might reach a stable solution much faster. So the first thing that you will realize here that this one will run for 1,000 iterations and the residuals get stalled. It's not like in the other solutions that you see that they're falling in a monotonic way. Here they're stalled. But remember, this is not an indication that the solution is wrong. Okay, this is the behavior coupled with the numerics, everything that is happening inside. So do not look at this, and this is something that I'm stressing a lot. Look also at monitors of integral quantities. So if we check now here our monitors, so see that we have a monitor for velocity, and see that this one got stalled about 100, let's say 200 iterations. If we go to velocity, see that this one is reaching a much faster steady behavior than the other one. So probably here we can say that in 7 iterations is already stable. So if you go back to the other solvers and you have velocity, see that in 700 still you need to let it iterate to converge. So this is the main difference between simple and coupled. So in theory they should reach, I'm not going to say that they should reach the exactly same solution, because you have different numerics on different treatments, but approximately they should reach very similar values. But the main difference is the convergence rate, okay? And coupled solvers tends to be much faster to reach a steady behavior. However, if you have some unsteadiness, probably they are not good anymore. And that's why this is why we don't use coupled solvers on steady simulations, okay? Because they're very costly. So you stay with the segregated solvers. And then we have different formulations of the couple. Okay, here you see that I got a style, but then I play around with the time scale factor. So here we have this one where we're using a low time scale factors, and see that now by using a low time scale factor, which is equivalent to reducing your time state, see that now we're reaching a monotonic convergence similar to the one that you have in the segregated solvers. But the problem that to reach this, it needs to iterate about 2,000 iterations. Okay, so it is converging. So now the cost of this one is more costly than a pressure segregated solver, and it reached, let's say, a steady solution at about 1,500. So the point is that now this seems much better, this one, because it's converging, but it's taking more time to reach the value. So if you start to compare those values here, you will see that all of them are very similar. Okay, but you see that now it's not very practical, this one. Okay, so you can reduce this time scale factor, but to stabilize the solution at the beginning, and then you can increase it. Okay, the value of 1 is a good choice. And now we go and we use the same, but it's a larger time scale factor. So it will be a time scale factor of 10. So we have this case, and see that now with a time scale factor of 10, see that everything is stalled. Very large time step. Your convergence monitors are worse than this one. This one are falling, but then are stalling. In this case, the situation is worse. Probably you will look at this and you will say, oh, okay, this is no good solution. But remember, this is not a true indication you are at a solution. You need to look at different fields. So if we look at the fields, see that now this one is introducing some oscillations. It's still the average values. As you go, they might be close to the actual ones in the other one, but where you have a small time set or a small under relaxations. Okay, see that probably this one is highly under predicted. So let's go back. Let's check mass flow. Okay, so about 4.5, and then this one, see that it's highly under predicted, about 3.9. Okay, so we start to see that you increase your let's call it your fictitious time state, but that is not giving you any benefit in your solutions. Okay, so it's not a good choice to go very large. Again, you can go very large if you see that this behavior is no good, you reduce it. But also what is interesting, look at the mass flow, is not perfectly balancing. Okay, it's going in a small value, but it should be much closer to 0. Okay, so you have some conservation problems. And we know that this kind of approach is pseudo-transient. There are a big violation of many physical principles, okay? Because we're advancing the solution using this local time step approach. It works, but it has the tendency, when you choose wrong parameters, it has the tendency not to conserve. And then we keep looking at here. So we have the solution we just ran. Okay, so see that we have everything. So here might be an indication that you need to run a little bit. See that it's oscillating. See that in the other cases, the couple is kind of converging at 4.5. And then just to show you the last solution, which is this was the Reynolds stress method. So you go here, you set up this one, then you use this method that probably is the classical one, okay, the simplest one. This will be the LRR, and then set up standard wall functions. Okay, you can use wall functions with Reynolds stress. However, it's not recommended. It's better to go wall resolvent, because we can see Reynolds stress models as it's called scale resolvent models. So I recommend you to go and do it wall resolvent. And your initial conditions. So remember that you need to give initial conditions. Your initial conditions are computing automatically, okay, for all your stresses. And if we look at the monitors, let me plot here. See that we have these monitors. So see that it's much expensive because you are solving more equations. Okay, so see that you are solving equations for k and epsilon that you need to get the epsilon in these equations that we saw in the theory. So you have 8 additional equations plus energy plus this one. You have scalars, you will have more equations there. So it's very expensive. Okay, and look at that, we have this behavior, okay, velocity at the outlet, it didn't converge. Okay, by the way, do not pay attention to this is a warning. So it's telling you that at the outlet you are having flow coming back. Okay, backflow flow. What is interesting, let's take a look at, I don't have it set, let me see the temperature field. So I'll click here, let me plot it and see what happens here. So see that kind of we have a bifurcation in this method. So its goal, it is oscillating around this value, which is close to the actual values that you get from all the other methods. So as we go here, y plus, so let me plot here again temperature. See that the value is something about 372 probably, and you check in the other cases will be around there. But look at here, it's about that value, but then suddenly, boom, you have this drop. And these are some of these elusive behaviors, strange behaviors that you can get with these methods. And probably you will need to let it iterate much longer, because probably you see that it seems that it have a long period oscillation. So maybe if you let it run for a really long time, it will settle around this value. But here you see that this model now is highly anisotropic. So this is what is happening here. It's computing all these structures, different methods, so it's getting different behaviors. You see, they are very, very expensive, and as I mentioned, it's better to use it fully on a steady. And when you post-process these solvers, just also look at the Reynolds stresses, okay? So as you go here, you plot those values in Turbulence, so you will have all your stresses. This is the quantities that you are going to plot. And just to remind you also as well, when you set boundary conditions, again, you have two ways to set it. You can use the K and turbulence intensity specification. So Fluent within have a method, the one also we show in the slides, that K can be equal to, let's say, the UU component is equal to K, the VV component is equal to 0.5K, and so on. Or you can manually define all your components, okay? So you need to have a lot of information, okay? Some detailed information, but usually this method is okay. So this is all, okay? So see that is a very nice case. You can play with different setups, so feel free to go around. So let me go and set up everything again like this, so we can just summarize everything, okay? You also here, you also here, and you also here. So as we go, see that different initializations and different solvers can give you very different behaviors in your residuals. The fact that your residuals are stalled is not an indication that your solution is diverging or is wrong, okay? So that's why you need to monitor some other integral quantities. So if we go now, and let me move now that I'm monitoring, let's say, velocity at the outlet, and if we put velocity at the outlet, velocity, okay, so if I go here, see that this one now, looking at velocity at the outlet or some other quantity, is a better indication. So see that different solvers will give you different behavior. So probably this is the ideal one, that about 500 or 600 iterations is already flat. Okay, this is what we want. Instead, in these cases, it's just you need to iterate a little bit more, or much more here to get it flat. Okay, so and in this case probably it's also flat. So see that they're all flattening about the same value. Okay, this one obviously is not okay, too large, the time scale factor. This one is, I can say that it's okay, it's flat, but probably we need to iterate a little bit more. So this one was very small time scale factor, so you need to iterate a lot. And then we just run this one. This one requires running more, okay? And your Reynolds stress tensors also, the values there are slightly different probably, but again, this one requires to iterate more, a lot, the Reynolds stress to get a good solution, a good stable solution. So that was all in this case. I hope you managed to reproduce. It's a very interesting case. The main idea here was this correction, okay, the curvature correction. So you can play around with all methods, and you will see all of them will give you different behaviors, okay. You can see also which one enables this curvature correction, and you can use the curvature correction, and you will see that always the curvature correction. In this case, it will limit the production of turbulent viscosity, okay. So if I would recall, just it's parallel matters, K epsilon and K omega have this curvature correction. They're probably the main groups of turbulence models. So that's all for this case. See you next time. Bye.